My name is Jesse Turner, and I'm a PhD student at Colorado State University. And I'm going to be talking about a collaboration between Colorado State and Vanderbilt, which is an open toolkit for animal-borne acoustic monitoring. And this is one of the awards that was for the WILDLABS Awards 2026. First off, I'd like to define the field a bit. When I talk about animal-borne acoustic monitoring, I'm going to be referring to it as audio logging, which is a term that's used by many practitioners, as well as one that encapsulates the constituent parts of the field, namely passive acoustic monitoring, which you all are probably familiar with, but just recording the soundscape around us, and biologging, which is when we attach sensors to individual animals. And so when we combine these two, we get audio logging, which effectively takes the scale of acoustic monitoring down to the resolution of an individual animal. And it lends itself pretty obviously to bioacoustic research because all vocalizations made by the focal individual are recorded by an audio logger. But there's also a wide range of other phenomena that can be detected, such as physiological sounds like respiration, anthropogenic noise impacts or impacts from other environmental noise. We can also record movement and feeding-related sounds and community interactions that are acoustically detectable. And I think what audio logging is enabling us to do is kind of a pattern that we've seen over the past decade or two with passive acoustic monitoring more in general. And that's a transition from being mainly detection-based to actually being able to resolve more information, such as behavioral information from vocalizations. So traditional uses of PAM largely have been, at least historically, extracting a vocalization from background noise and using that presence of the vocalization to determine presence, absence of a species, perhaps abundance or distributions in space or time. But as machine learning and computation has increased, we've been able to extract additional information from vocalizations because they are honest signals that encode a lot of biologically relevant information. But we need context in order to make that association. And with wild animals, that is often very difficult to get that context with traditional systems. But audio loggers can provide that context. So we can look at behavioral bioacoustics, or when specific vocal behaviors are correlated or can be used as a proxy for specific behaviors. We can also look at correlations between vocal behavior and movement. It's very common for audio loggers to be as part of a multimodal system with either GPS, which allows us to look at large-scale movement, or accelerometers, enabling us to look at fine-scale movements. And also we can assign vocalizations to a particular individual, which can be very difficult with traditional acoustic monitoring systems. We can also look at responses to environmental noise. So everything that the audio logger is recording, the individual animal is also hearing. So if there's any response to an environmental noise, whether it be from humans, other animals, or the general environment, we can research that as well. So the real gap right now is that there's no off-the-shelf or open source audio logger systems that exist today. And so this leaves us with two different possibilities. We can either modify existing off-the-shelf systems, which this team to the left has done by attaching a voice recorder onto a collar deployed on a Panda. But these are not going to be optimized for the task. They might not be as durable as they need to be. They're probably not as power efficient as they could be. And so they're not perfect for the situation in which they're being deployed. And on the other end of the spectrum, we have fully custom systems. And so we have a team there on the right that deployed a custom audio logger on an African lion. And these are obviously very optimized for the task, but they require pretty significant resources and expertise in order to develop a system like that. And that's something that most teams that are interested in this sort of research don't have the capabilities. So our solution to this is an open source audio logger system, an end-to-end toolkit that's based around the Apollo 4 microcontroller. You can see a picture of the board on the bottom right there, which boasts a low power consumption, configurable sample rate between 8 and 48 kilohertz, and an onboard accelerometer that enables us to detect those fine-scale movements. We've incorporated a variety of features to make it as easy to use as possible, namely a removable SD card that is both used for data storage as well as configuring the acoustic settings. It writes uncompressed WAV files, meaning that no proprietary software is needed for downloading and listening and analyzing the acoustic data. And a simple magnet can be used for activation and deactivation. A key feature of our system has been a modular approach. So we've realized that there's a wide range of different species that this could be applicable for, with different sizes, different attachment mechanisms. And so having a modular approach enables us to be flexible depending on the application. So we have CAD designs for 3D printed housings that can be modified depending on the size. Additionally, battery packs can be increased or decreased in size depending on the requirements for lifespan and weight. The board can be used with either analog or digital microphones, and we've been experimenting with a variety of different drop-off mechanisms because the GPS collars themselves generally last a lot longer than the audio loggers do. And so a drop-off mechanism enables us to collect those data before the collar is actually removed. And so I have pictured below just a couple of examples, a mule deer deployment on the left in Colorado, which had a 3D printed housing, an analog microphone, and no drop-off, so it was just permanently attached. And then on the right there is a deployment on an elephant, which we used an aluminum housing, a digital microphone, and integrated it with a Telonics drop-off mechanism. So I'd like to touch on the adaptive data collection aspect of the board. But first, I want to briefly mention why we wouldn't just continuously record audio. It's kind of obvious, but if we're continuously recording, the more data we're collecting, we're going to run out of power and storage faster. So we're going to decrease the lifespan with continuous recording. But more importantly, we're gathering a lot of irrelevant data. So it's pretty rare that an acoustic monitoring project will actually use all of the acoustic data. Generally, we use a very, very small subset of the data. It's just that the trick is with embedded systems, it can be tricky not to discard the relevant data that we actually want to retain. So to that end, we have implemented and are also developing some different strategies in order to not just be continuous recording, which is a possibility. So on the left there are some data reduction techniques that are more standard and you might be familiar with, such as amplitude thresholding to discard periods of relative silence, as well as frequency band triggering to only record time periods when there's some activity in the frequency band of interest, and time-based filtering like duty cycling and scheduled recordings. And all of those have already been implemented on the device. And on the right side, we have a couple of more intelligent data collection strategies that are in development. More specifically, a variational autoencoder, which effectively translates a sound into a numerical representation where similar sounds will have more similar representations. And then we can have a decision tree on whether to record or discard those data, depending on, for instance, cluster density, which would be indicative of how rare or common that sound was. So we could only record more rare sounds and discard common sounds that would probably be background noise. We also have the capabilities of more computationally intensive classifiers to run on device, but generally these use more power than continuous recording does. So they're useful in reducing the total amount of data, but not in reducing the actual power consumption. But still, for our larger systems with bigger battery packs, we're effectively storage constrained for those systems. And so this technique could still be useful in extending lifespan. I'd like to highlight a few case studies of focal species that we've been deploying on. So this is the African savanna elephant, where we are conducting a study on vocal communication. Specifically, we are monitoring call rates and looking at the correlation between vocal and movement behavior. We've deployed a total of 19 different systems, and out of the systems that we've recovered, we have a max recording duration of 36 days. However, those systems were on a much less power efficient firmware. So the ones that we're currently recovering, we anticipate about 120 days or 4 months of continuous audio. Another focal species has been bighorn sheep. And the purpose of this project is actually disease monitoring. So we are acoustically detecting coughs as an indication of respiratory disease. which is a big problem in bighorn sheep in the Mountain West, where pneumonia is a pretty significant cause of mortality, and also can cause acoustically detectable coughing symptoms. We've deployed 5 total systems on bighorn sheep and have a maximum recording duration of 45 days. And the last case study I wanted to highlight is a collaboration with the Scandinavian brown bear research project, where we are deploying a few systems on brown bear. And that team is actually interested in acoustically characterizing predation events. And we've deployed 5 systems on brown bears, and the recovery is currently in progress, but we anticipate at least 40 days of continuous audio coming from that system. So although all of those projects have so far gone smoothly, they've required a significant amount of resources and time from our team. From customizing the housings to attachment mechanisms, also configuring the acoustic settings, and testing the fully end-to-end systems. And this is just not feasible on a larger scale or in the long term. So we're in the process of developing 3 different template sizes for different species, where we have a small, a medium, and a large, with the goals for design specifications listed here in terms of weight, recording lifespan, housing material, and build cost. And I'd like to point out that the recording lifespan there, that's based on continuous recording. So if we utilize any of the data reduction strategies that I previously mentioned, then we can greatly extend the lifespan of those systems. Another front that we're pushing forward on is the software development. So we are working on refining the firmware in hopes for more power efficiency gains, as well as direct integration of the audio logger board with GPS collar systems from Savannah Tracking. We're also creating edge models, both supervised models for on-device classification, as well as unsupervised models like the variational autoencoder, which can be useful in more intelligently deciding which data to store versus discard, simply based on the soundscape in which is deployed. And lastly, we'll also be working on the configuration interface. So pictured to the right there is a screenshot of the graphical dashboard that will be continuously updated and made more user-friendly as the project moves on. And for our team and for Wild Labs, open source is really a key focus. So all of our software and firmware is on GitHub and will continue to be updated as we move through the project. We'll also be developing assembly guides and manuals that will be publicly available for how to use the system, and CAD designs for the housings that can be either used directly or easily modified if the size or the design is slightly different depending on the application. And any AI models that we develop as a part of this project will be released to Hugging Face. So we're looking for collaborators who are interested in pilot deployments. So if anybody is hearing this and thinks it could be applicable for their system, please reach out. And pictured to the right there is just our GitHub account with all of our software and firmware. So that's all I have. Thank you guys so much for your time. On the right there is a QR code that you can scan, which will take you to our website where you can get some more details about the system. My email is also listed there if you'd like to reach out. We're specifically interested in hearing if there's any specific development that would make this system more usable for your application, or if your team would be interested in testing a pilot deployment. We'd love to hear from you and potentially start a collaboration. So thank you guys very much.
Thank you very much. Another great talk. We do have time for questions. I don't see any questions in the chat right now, but I have some from my team. Which species or taxonomic group do you think stands to benefit the most from this technology over the next few years?
Good question. I think, we have noticed, like, in terms of the attachment mechanism, GPS collars, lends itself really nicely to this work. And so I think GPS collars are really going to be the attachment mechanism that we're going to be focusing on. And to date, we've largely focused on, at least internally, on ungulates. So I think that's going to be the species that we're going to be mostly focusing on. However, we've also had other teams, like I mentioned, that brown bear project that is, also using it for acoustically characterizing predation, and so it definitely works for carnivores and other species as well. But I think ungulates are probably going to be our focal taxonomic group.
Great, thank you. I did see a question from Nathan. Do you have any plans to integrate with Iridium or anything similar?
Yeah, so I mentioned briefly that we're directly integrating the audio logger board with a GPS system, and so a GPS collar system, specifically one from Savannah Tracking. And so the end goal is to not have the audio logger itself actually directly connect with Iridium, but instead integrate the audio logger board so it directly actually connects with the satellite system that's already being used by most GPS callers. So instead of reinventing the wheel, we're hoping to be able to more directly integrate with systems that already have that capability. But what that would enable us to do is any sort of real-time alerts. And so there's a couple of instances that we're interested in, like gunshot detection for poaching, or it doesn't have to necessarily be gunshot, but just human sounds that where there shouldn't be human sounds. And then also for instance, the bighorn sheep system, cough detection. If we had a system that where it could detect a certain threshold of a number of coughs per day, then we could, in theory, have an alert that says, "Oh, there's a potential outbreak that's about to happen based on acoustically detectable symptoms."
Great, thank you. Another question from my team. What would success look like for this project as an open source community rather than just a research project? How do you hope other researchers will contribute?
Yeah, so that's a great question. I think success for us looks like the ability of teams to be much more autonomous in their use of this system. All of the deployments that we've done to date have been extremely labor intensive from our team, which has been by design because we want to be involved. But as we scale up and deploy on more systems, that's not becoming feasible. So what we're hoping is that we can kind of take our foot off the gas and not be as directly involved. We'll obviously still be available and in contact for any issues or concerns. But I think for us, success looks like people being able to autonomously deploy these systems on their own without a lot of input from our team.
We have some time before the end of the call if there are any other questions. Jesse, have you encountered concerns about filtering out data on the edge?
Absolutely. Lots of concerns. Yes. That's why the more standard data reduction techniques that I mentioned, the ones, amplitude filtering, frequency-based triggers, those are not like intelligent data collection methods. And that's why we're, still developing the intelligent data collection methods, because it's not only, a matter of filtering out data at the edge, but it's also because these are animal-borne systems, they're not the acoustic data don't look like most other acoustics projects, right? Because we have sounds from rubbing on the system or from breathing, and so it's hard. It's like there's a lot less silence than you might think because there's all those interferences, and so we've definitely had a lot of issues with filtering out data, but we're confident that that some of these, like the variational autoencoder, for instance, can be still useful in particular systems. And I don't think it's going to be like a reduction of like 95% of the data, but it could be a reduction of something more like 50% of the data, which would still could potentially double the length of the deployment. So still useful, but yes, we've definitely encountered a lot of issues with filtering out the relevant data that we want to keep.
Another question from Frank. Frank, do you want to ask this one on the mic?
Yeah, I guess I was just curious about because obviously every sort of area and environment for these species, I imagine can encounter, environmental challenges as far as like device longevity and, protection for the device just from working in like a rainforest habitat. So I was just curious as far as when you design the, protections and things for that device, if you have to consider specifically factors like cold or humidity or even behaviors like from the focal species itself that could damage the device.
Yeah, absolutely. So we've deployed a couple of systems on caribou in winter up outside Fairbanks, and so that was probably the coldest side of things. It was obviously very very cold up there, and we did encounter some issues with the analog filter or the analog microphone that we were using at the time, and it was basically failing because of the temperature, and so our batteries, I did a lot of research to make sure that the actual cells we were using would be fine. And obviously we, decreased the lifespan by quite a bit in those temperatures, but we were still able to record data. But yeah, we noticed that the analog filter in cold temperatures, or the analog microphone, excuse me, in cold temperatures was problematic. But I think, the goal right now, all of our systems have been potted. So we're less concerned about humidity, water, temperature because the temperature is obviously still getting there, but because we're potting all of our systems, we're not as worried about, water intrusion or capturing, humidity in the air when we close up the system. And I'm definitely thinking about different strategies for that because when you introduce potting, that makes open source systems a lot more difficult to manufacture. And also it also increases weight. But we found that especially for some of the more difficult systems, like for African elephants, for instance, that is a very, very tough system. But we so far haven't had any actual mechanical failures of the acoustic board or the acoustic system itself because we've been potting and using aluminum housings. But I think, yeah, in the future, if we are able to, design a system without potting, I think we'd still want like some sort of desiccant inside the housing because yeah, it's always, especially in rainforests. I mean, you always, you get the water or you get the air in the housing, and then the temperature changes, and then yeah, all the rest everybody knows about. So, but yeah, I think potting compound has really been a lifesaver for us on that front.
Well, thanks again. That was a brilliant talk. Thanks very much.